Hi, my name is Richard. I'm working for GDA, and today I'm going to do a video on the possible benefits of using neuromorphic technology with photonics, and it's going to be quite interesting. But we're going to put in a financial use case. So the financial use case we're going to put in is algorithmic trading over 1 minute intervals, or it could be 30-second intervals. Or even less actually. We have to link this into the kind of crypto data initiative that we're doing, where we're providing this kind of data, especially when we're looking at, and we touched on this in the last video, so if we look at the previous video that we did, it kind of touched on the supply and demand and all the different events in the limit order book. So let's start talking about reinforcement learning. It's unsupervised. It's based only on the rewards from actions and how the system reacts. As in continuous time stochastic control, the actions affect the rewards and systems. So reinforcement learning is kind of the intersection of stochastic control and machine learning. Because we can apply deep neural networks to our, we can have deep neural network reinforcement learning. We can have double deep neural network reinforcement learning. We can have Kalman filter or reinforcement learning with Kalman filters. So there's a whole kind of suite of reinforcement learning algorithms that we can use in algorithmic trading. So it can be model free. The goal is to maximize the performance criterion. We've got a number of states of the system at time t. A is all the admissible sets of actions, and the system evolves over S and st plus 1. Now, talking about the data features, we're collecting all these different events. So normally we get 3 events, but we've managed to kind of work out in real time what the original 8 events are, and that allows us to have many data features. But I mean, not only are we looking at the kind of volatility of the data, we are working out the volatility, but we're also working out for example, the volume of new order buys, the volume of new order sells, the rate of cancel to buys, the rate of cancel to sells, the volume of cancel buys, the volume of cancel sells, and the rate of delete to buys, the rate of delete to sells, etc., etc. And we're doing that over 100 millisecond intervals. So we're actually going under a second. So because when we look at things like order flow imbalance, that is the kind of additive. That the supply and demand, those kind of metrics are additive. We can add, we can add all these data features. So it's not an issue for us to kind of aggregate them from 100 milliseconds, 500 milliseconds, 1 second, 5 seconds, 30 seconds, up to a minute. But supposedly we'll be running our trading algorithms at about a minute, so we're getting all the volumes over 1 minute. And the associated rates. So in Q-learning, the transition properties are known. You can solve this as a fixed point equation for the value function. You can simply iterate it and get it. But the point is, we don't want to make an assumption on the transition probability. That's why, that's in reinforcement learning, and that's where Q-learning comes in. So let's we can rewrite the Bellman in terms of the state action value, and we can get a Q Bellman-like equation. Again, this is a fixed point equation for Q. The goal is to estimate this function and the optimal actions just from the data. Now, in deep, when we're using a deep kind of Q learning approach, the idea is to minimize the loss of the Q function, which we use a one-step Monte Carlo but over many samples, it's hoped that this converges to a fixed point of the Bellman equation, although there's no proof of this, but it's just kind of common sense. It's just just the kind of approach taken. Now, when we use normal CMOS technology, there are limits of scaling in terms of heat and wall memory. So as we increase the clock frequency, that increases the heat. So we can see that very soon, if we were to carry on the same trajectory that we were on, we'd end up at the same heat as a nuclear reactor in terms of power density and clock frequency. We can see that the brain is down on the left bottom corner, and it's got a very low clock frequency and it's got very low power density, which means it's extremely efficient. In terms of memory, we've got this memory wall bottleneck between the CPU and the memory. So these are kind of suite of current CMOS technologies. For example, we've got our ASIC chips over here, which are used in mobile devices. We've got our FPGAs, which are used in automotive industry. They're also used in high frequency trading. We've got our GPUs, and we've got our tensor processing units. You'll notice that the brain is processing a hell of a lot of more, orders of magnitude more GOPS per second, and it's using only 20 watts of electricity. So the answer is we can't shrink the transistors anymore because we're getting down to countable lanes of traffic. So this is a transistor, and these are the electrons. About 5 nanometers electrons start to repel each other, so there's only so many electrons you can fit in a lane. You can increase the height as well, but again, you know that you are limited. So this limit is called the von Neumann wall, and we're going to kind of show what that is and talk about it. But first of all, let's discuss neuromorphic computing. Okay, so the first step is to co-locate your memory and your processing. So in digital computers, CPUs, GPUs, TPUs, and FPGAs, we've got a huge, power density of 100 watts per square centimeter. So if you look at the brain, the neurons do the processing, and the synapses hold the memory, and it runs on 20 watts of electricity, as discussed earlier. So it's incredibly more efficient. Yes, we are moving towards kind of system on a chip architecture, but still, there's still going to be this kind of maximum the amount of efficiency. Like if you were to look at the fastest computer in the world at the moment is I think is a Japanese computer, and that uses a kind of system on a chip architecture, and that can manage one EFLOP, but it uses half an EFLOP. That uses a tremendous amount of electricity, while your brain can process up to the equivalent of one EFLOP for 20 watts of electricity. So deep learning is huge in the cloud. Backpropagation training is powerful. Networks are deep in space and time. So space is actually discretized into layers, and time is discretized into steps. So there's a clock which can run, and that clock in the CPU is basically it does an operation at each point. Now, if we look at one layer of N neurons connected to another layer of N neurons, like any typical neural network, we get about N squared connections. This is a classical neural network, which you use when we're training for backpropagation. Backpropagation tells you the weight at which each neuron is connected to the others. So if the neuron is active, you times it by some weight until it is the input to the next neuron. Time is discretized, so you weigh one time step and proceed. So for each time step, you can work out the energy of an update, as it being the number of connections times the active neurons times the multiply accumulator. Now, in terms of temporal sparsity, CMOS architectures, like GPUs, tensor processing units, or FPGAs, don't take advantage of temporal sparsity. So if there is a non-active neuron, if we're doing some kind of tensor multiplication, that will still get multiplied, so that will still use energy. But in a brain, because we use spiked neural networks, and if a neuron is not active, it won't be used. Therefore, that massively kind of reduces the energy per update. So that's temporal sparsity. And of course, spatial sparsity will get reduced as the number of connections go down. So then obviously the energy per equivalent synaptic operation becomes massively reduced. We can see as as we decrease the number, or as we only select the active neurons, the connection goes down from 6 to 8, and that's just looking at temporal sparsity. And we can have spatial sparsity, which again, reduce the number of connections to 4. So we've gone from 16 to 4, which is quite a reduction. So we can see why these neuromorphic chips are much more kind of efficient than what we've got at the moment, or what we, this CMOS architecture. Now, before World War II, we had analog computers, and then after World War II, we went to digital computers. Now, mechanical computers and digital kind of computers, we have to kind of break them down into computation and communication. So, prior to World War II, we had analog computation, analog communication. In the modern age, everything is digital, so digital communication and digital computation. So if we look at the brain, it kind of sits in this quadrant. So it's communication is digital, but it's computational is analog. Analog is good for computation as it degrades more gracefully with noise. So it's again more efficient. This is kind of going into event-driven operations. So in the brain, there isn't this kind of central processing clock spinning very quickly and shooting out loads of operations. Everything is event-driven, which again is much more efficient. Again, this is I'd like to kind of finish off looking at this diagram, and we can see that we've been talking about this kind of von Neumann efficiency wall, and we can see all the kind of CMOS digital electronics over here, and we can see microwave electronics here, which is got a faster computational speed. But what we've got to be aware of is that, okay, we've got this neuromorphic electronics, which is, yes, it's more efficient, and we've got this silicon photonics, which is almost as efficient but much quicker. And we've got the human brain, and then we're kind of going on to neuromorphic photonics. But there's the issue of scale. How do we shrink everything down? So if we look at the kind of synapses in the brain, they're on the kind of 10 to 20 nanometer scale. So how do we shrink our kind of neuromorphic photonic circuitry down to that kind of level? Well, the kind of, first of all, let's break this down into the photonic side of it. Okay, so if we're looking at some spikes, and we're looking at kind of biological spikes, they happen in the range of 1 millisecond, and there's about a 100 millisecond gap between them. If we're looking at kind of digital circuitry for a spike, we're looking at anywhere in the region of 100 nanoseconds, and there'd be a 10 microsecond gap. But if we're looking at photonics, then we're looking at 10 picoseconds, which is a ridiculously short amount of time. I think it's a time that light can travel in 30 millimeters or something something like that. And the gap between them is 1 nanosecond. So obviously the photonics spikes are much quicker. Now, but we've still got the human brain over here, which is incredibly efficient, and these neuromorphic photonics are not able to kind of scale to the same size as the neurons. But there's another good thing. Apart from this speed, it's we've got an evolution of the field towards photonic plasticity, which is one of the most appealing features of the kind of neural systems is plasticity, i.e. the natural ability to learn and adapt to an unpredictable and changing environment. So that's the ability to change to a different kind of regime, a different market regime for our reinforcement learning algorithms. So if we're using these kind of chips, they'll be able to do that quicker. And it's a vital stage towards developing truly biorealistic photonic neuromorphic hardware as a photonic implementation of plasticity in artificial synapses and neurons. But if you may have noticed this kind of red square here, which is the crazy square. I mean, this is crazy because this is kind of like we're using technologies where we can actually get our neurons down to the same size as a human, but we've also got this, so we're just as efficient as a human brain, but we're orders of magnitude, many, like, was it 12 orders of magnitude faster? So we've talked about the computational speed and how photonics is supreme. Now we've got a kind of issue, the final kind of barrier, and that is to, as you can see, at the moment neuromorphic photonics is not as efficient as the human brain, and that's because we've got to basically shrink the mem resistors down to the same kind of size as biological synapses, which is about 20 to 40 nanometers. And the way we're going to achieve that is by using a graphene-based or graphene oxide-based laser patterned photonic mem resistors, with sizes comparable to those of the biological synapses. That's 20 to 40 nanometers will require fabrication methods, or this will require fabrication methods which are able to go beyond the diffraction limit. Technologies such as super resolution photoinduction inhibited nanofabrication, or SPIN for short. So this is what we mean by the kind of super resolved neuromorphic photonics, and this would be just as efficient as a human brain, but 12 orders of magnitude faster, which is unbelievable. So these neurons will be able to scale as well. So scalability is a very kind of big important factor. So if we were able to build a brain, it would be just as efficient, just as adaptable, but able to learn 12 orders of magnitude faster than we would. So there's kind of food for thought in that. Okay, lovely. And then we'll do our next video. We'll be out soon. Thank you very much.